Your A-level chemistry exam is in 2.5 months. What do you know about buffers? A buffer is a solution which resists changes in pH when small amounts of acid or alkali are added. And it resists changes because there is a large reservoir of weak acid and conjugate base or weak base and conjugate acid. And this weak acid and conjugate base will react and neutralize the added alkali and acid, and in doing so it prevents the pH from changing. I've also told you that a buffer is a solution, and there are two types of buffer solutions. There are acidic buffers and there are basic buffers. An acidic buffer is made from a weak acid and its conjugate base, and a basic buffer is made from a weak base and its conjugate acid. An example of an acidic buffer would be ethanoic acid, a weak acid, and its conjugate base ethanoate. An example of a basic buffer would be ammonia, which is a weak base, and its conjugate acid ammonium. So our buffers can therefore be represented by an equation. A typical equation you'll see is HA goes to A minus plus H plus. I told you earlier that weak acid and conjugate base react with added acid and alkali to keep pH constant. And I'm going to show you exactly how that happens with these two examples. Our buffer here is made from ethanoic acid, the weak acid, and sodium ethanoate, where the ethanoate is our conjugate base. And the buffer would look a bit like this. It would have our undissociated ethanoic acid alongside the conjugate base ethanoate, and there'd also be H plus in the solution as well. Our equation for this buffer would look a bit like this. Ethanoic acid, which is our undissociated acid HA, goes to ethanoate, which is our A minus, plus H plus. And this reaction is reversible. And it's important to remember that buffers are equilibriums, and therefore they will be governed by Le Chatelier's principles. In this first example, we've added acid to a buffer. So all we're really adding is we're adding H plus into our solution. And when we add that H plus into our solution, the overall concentration of H plus in our solution will increase. So the right side of our equation is going to increase, and Le Chatelier's principles will tell us that the equilibrium will act to counteract the increase on the right side of our equilibrium. So therefore, our equilibrium is going to shift left and produce more undissociated ethanoic acid. So what happens is the excess ethanoic acid in our solution will react with the H plus to produce more ethanoic acid. And in doing so, it is neutralizing the added acid and therefore preventing the pH from decreasing. And our pH here is going to stay relatively constant and only change within the buffer's pH range because there is a large reservoir of both undissociated acid and conjugate base. So the overall concentrations change very little. And you'll see here I've provided an explanation for you to use in your exams. In this second example, we have the exact same buffer, so the equation of our buffer will remain the same. And so will our solution as well. Our solution will have our ethanoic acid, our ethanoate ions, and our H plus. But this time we're going to be adding a base and alkali. And you know that a base and alkali accept H plus. And so an example of this is us adding hydroxide ions into our solution. And when we add a base like hydroxide, it's going to react with our H plus. So here the H plus will combine with our hydroxide ions that we just added in to form water. And the overall concentration of H plus is going to decrease. So this right side of our equilibrium will be decreasing. And if we use Le Chatelier's principles, we know that this equilibrium will act to counter that decrease in our H plus. So the equilibrium is going to move right and shift to the right. So our ethanoic acid is going to dissociate into ethanoate and H plus to counteract the decrease in H plus when our base was added into our solution. And in doing so, it will allow our pH to remain constant. And because we have this large reservoir of ethanoic acid and ethanoate, the overall concentrations will change very little. They'll remain relatively constant. And so our ratio of acid to conjugate base will remain relatively constant, and that will mean that pH stays very similar. The Henderson-Haselbach equation. The Henderson-Haselbach equation looks a bit like this. pH of our buffer solution is equal to the pKa of our weak acid plus log base 10 concentration of conjugate base in our solution over the concentration of undissociated weak acid in our solution. And we get this equation from a sequence of rearrangement and substitutions to the Ka equation, which I will show here. Feel free to have a look at that in your own time. I did say earlier that the Henderson-Haselbach equation can provide us with an explanation for buffer actions. And the theory looks a bit like this. In our equation for pH, for pH to remain constant, the ratio of weak acid to its conjugate base must also remain constant. As long as environmental conditions are the same throughout, the pKa is always going to be constant. So we know that the pKa isn't going to affect the pH of our buffer. So the only thing that can affect the Henderson-Haselbach equation is that ratio of weak acid to conjugate base. And the reason that ratio can stay constant in our buffer is because we have a large reservoir of both weak acid and conjugate base. So we have an excess of these two. So changes to the concentration of weak acid and conjugate base have minimal effect on the overall concentration of the two. And so that is why that ratio will stay relatively constant throughout, and hence why our buffer will resist changes to pH. Finally, the Henderson-Haselbach equation is only an approximation. It assumes things. One of the assumptions that the Henderson-Haselbach equation makes is that our buffer solution has a sufficient concentration of HA and its conjugate base so that when water dissociates into OH- and H+, the concentrations of HA and A- are changed minimally, and so the pH will remain relatively constant. And this is because those hydroxide ions and those hydrogen ions will react with weak undissociated acid and its conjugate base, and in turn it will alter their respective concentrations and therefore change pH. But as long as there is a sufficiently large concentration of our weak acid and its conjugate base, this reaction between the hydroxide ions, H+, and the weak acid and conjugate base can be ignored. Another assumption of the Henderson-Haselbach equation is that the acid used is sufficiently weak so that when our buffer reaches an equilibrium, that weak acid has dissociated in very small concentrations of H+ and its conjugate base. By dissociating, the concentrations of weak acid and conjugate base would change. But because our acid is sufficiently weak, the concentrations of our acid and its conjugate base will remain the same at the initial point and at the equilibrium point. On the screen, you will see some scenarios you may come across in a buffer calculation. These scenarios are the context in which a buffer is made. In this first scenario, our buffer is made from a weak acid solution and a salt solution. And it's done by combining 50 cm cubed of ethanoate of concentration 0.25 moles per decimeter cubed, which is added to 40 cm cubed of sodium ethanoate of concentration 0.15 moles per decimeter cubed. The Ka of ethanoic acid is 1.5 times 10 to the minus 5. Determine the pH of the buffer. When we combine these two salt solutions, we are increasing the volume to 90 cm cubed, but we are keeping the moles of ethanoic acid and ethanoate the same in that solution. So the concentration of ethanoic acid and ethanoate is going to change, so we need to work out the new concentration of ethanoic acid and ethanoate. So there are two ways to do this, but I'm going to use the easier way, which is using fractions. I know that the total volume of our solution is 90 cm cubed. 50 cm cubed of our 90 cm cubed is made using ethanoic acid, and I know that 40 cm cubed of our 90 cm cubed is made using ethanoate. So using that information, I'm going to make two fractions to find the new concentrations of ethanoic acid and ethanoate. So I'm going to do 50 over 90, which is the same as saying 5 over 9, times 0.25, and this is to work out the new concentration of ethanoic acid, which is going to give me a concentration of 0.13889 moles per dm cubed, and that is the equivalent of 5/36. I'm going to use this value here in my calculator. I'm going to keep this value on my paper, and we're going to do the same now for ethanoate. So 40 over 90, which is the same as saying 4/9, times by 0.15 gives us 0.0667 moles per decimeter cubed, and that is the equivalent of 1/15. So using these exact values, I'm now going to calculate the concentration of H plus in our solution. And I'm going to do it using the Ka equation. So let's write the Ka equation quickly. Ka is equal to the concentration of H plus times by the concentration of A minus over HA. I'm going to rearrange this to get Ka times undissociated acid over conjugate base, which is equal to the concentration of H plus. So using my new concentrations alongside the value for Ka, I'm going to work out the concentration of H plus, and that will give us a concentration of 3.75 times 10 to the minus 5 moles per decimeter cubed. And from here, it's very simple to work out the pH, because I know pH is equal to minus log base 10 concentration of H plus. So I'll just plug this number into our formula, and that will give us a pH of 4.425968732. And I'm going to round that to the same significant figures we find in our question, which is 2. So I'm going to round that to 4.4, and it's that simple. So when the scenario involves a weak acid solution and salt solution to make our buffer, you need to work out the new diluted solutions, work out the concentration of H plus in our solution, and then you can work out the pH from there. In this scenario, we are using a weak acid solution, and we are dissolving a solid salt into this weak acid solution to form our buffer solution. In this question, 1 gram of sodium ethanoate is dissolved in 50 cm cubed of ethanoic acid of concentration 0.25 moles per decimeter cube. We're given the Ka equation, and we're asked to find the pH of the buffer. Our first step is to work out the moles of sodium ethanoate dissolved in our solution of 50 cm cubed. So, in order to work out the concentration of sodium ethanoate, I first need to work out the MR of sodium ethanoate, which is 82. I'll divide the 1 gram that we've dissolved in by 82 to give us 0.01219512195 recurring. From there, we will use our value for the number of moles of sodium ethanoate to work out the concentration of ethanoate inside of this 50 cm cubed solution. So all we're going to do is we're going to divide our number by 0.05 decimeter cubed, which will give us 0.24390 moles per decimeter cubed. For a more specific value, it is 10/41. And this is the value I'm going to use in my calculator so that I can get an accurate pH. From here, we're going to use the Ka equation to work out the concentration of H+. So let's rearrange the Ka equation, solve for H+, which will give us Ka times Ha, the acid, over the concentration of conjugate base, which equals the concentration of H+. So subbing in our numbers of 0.2439 alongside the Ka value and 0.25, that will give us a concentration of H+ of 1.845 times 10 to the minus 5 moles per decimeter cubed. From there, I know that pH is equal to minus log 10 concentration of H+, and so I'll sub in our value for the concentration of H+ into our equation, giving me a pH of 4.734. In this scenario, we have a weak acid solution added to a strong base solution to form our buffer. And here we have 50 cm cubed of NaOH of concentration 0.13 moles per decimeter cubed, which is added to 50 cm cubed of ethanoic acid of concentration 0.25 moles per dm cubed. We've been given the Ka and we want to work out the pH of the buffer. When we add NaOH to ethanoic acid, we're adding a base and an acid. So you already know that there is going to be a neutralization reaction that occurs between the two. So that strong base NaOH and that weak acid ethanoic acid will react together. So the first step here is we need to work out what's actually going to happen when those two solutions get added. And so let's write down that equation. So we are adding NaOH to ethanoic acid. And I'm going to remove this sodium. So I'm going to just work with our hydroxide ion. And we know that this base here will accept H+, and this acid here will donate H+. So we know that this OH is going to accept H+ and go to H2O, and that our acid is going to become deprotonated and form ethanoate. And it is this ethanoate, which is formed from this neutralization reaction, which will form the conjugate base involved in our buffer. Now, because this is a neutralization reaction, I know that some of this acid is going to get used up. And so we need to first work out the remaining concentration of this acid. So let's do that. Our moles of OH minus is 0.05 decimeter cubed times 0.13 moles per decimeter cubed, which will give us 0.0065 moles. I know the moles of ethanoic acid next. It's going to be, once again, 0.05 decimeter cubed, because that's how much ethanoic acid there is. And it's going to be multiplied by the concentration of ethanoic acid, which is 0.25 moles per decimeter cubed, giving us 0.0125 moles. And I can see here that this hydroxide ion is going to get used up first. So our ethanoic acid will be the only reactant remaining. So let's work out the moles of remaining ethanoic acid. So what we're basically doing is just a subtraction of 0.125 minus 0.0065, which will give us 0.005. 0.06 moles of ethanoic acid remaining. Next, we need to work out the moles of ethanoate that is going to be in our solution. It's a 1-to-1 ratio of OH- ions to ethanoate ions. So the moles of ethanoate is going to be 0.0065. The next thing we need to do is just work out the concentrations of these two in our solutions. Our overall volume is 100 cm cubed, so I'm just going to divide both of these by 0.1. If I do that, that will give us 0.06 moles per dm cubed, and that will also give us 0.065 moles per dm cubed. From here, we can now use the Ka equation to work out the concentration of H+. So we can just plug in our values into our equation. So that will give us a concentration of 1.66 times 10 to the minus 5. I'm then going to use the pH equals minus log 10 brackets the concentration of H+, giving us a pH of 4.7795. And it's that simple.